JWST recently measured the temperature of an exoplanet. But how? How is that even possible? Here's how astronomers can do this. You may remember an announcement back in 2017 when the Spitzer Space Telescope found 7 Earth-sized planets orbiting a single star about 40 light-years away. This was the TRAPPIST system, and we've been studying these planets closely ever since. Finding an exoplanet is actually surprisingly simple. 3 of these exoplanets were first detected by Chile's TRAPPIST telescope. This robotic observatory uses the transit method to detect dips in the brightness level of a star. These dips are often, but not always, caused by a planet passing in front of the star as seen from Earth. It's basically monitoring for and measuring these eclipses. There are other ways to look for exoplanets, but the transit method is the most common one. TRAPPIST-1b is the innermost rocky planet orbiting its host star and M dwarf star. It's not in the habitable zone. But we are specifically interested in these types of stars because scientists have found that they are twice as likely to have rocky planets orbiting them than stars like our Sun. And there are 10 times as many of them in the galaxy. The caveat is that these stars are also much more active than our Sun. Their solar flares and X-ray emissions could strip a planet's atmosphere. That's why astronomers are looking so closely at the TRAPPIST system, because it may be representative of the many other star systems like this within our galaxy and universe. It's helpful in our search for other habitable worlds and alien life. The temperature of a planet is a good indicator of whether or not it has an atmosphere like our own. This planet is tidally locked, which means it takes the same amount of time to rotate on its axis as it does to orbit its host star. Think of the moon, which is tidally locked to the Earth, so we only ever see one side of it from here. One side of TRAPPIST-1b always faces its host star. If it did have a puffy atmosphere like the Earth's, then the temperature of the side facing the Sun would generally be cooler than if there was no atmosphere, because the atmosphere would circulate and redistribute the heat across the planet. Scientists use JWST's MIRI, or mid-infrared instrument, to measure the brightness from what's called a secondary eclipse. Infrared is basically heat energy. When the TRAPPIST-1b planet is between the Earth and the star, that planet's heat is added to the star's heat. It's hotter or brighter when we can see the planet than when we can't. When the planet is behind the star appears to us as cooler or dimmer because it doesn't have the additional heat from the planet. And if you're saying to yourself, well, planets don't actually give off heat, we're talking about the heat from the side of the planet that faces the star. A secondary eclipse is when a planet moves behind its star. Scientists measure the change in brightness and heat energy from when the planet was visible and then when it wasn't. They could then calculate just how much energy is coming from the side of the planet that faces the star and then calculate the temperature of that day side. You can see a visual representation of that here. The blue squares are individual brightness measurements through MIRI's F1500W filter, which only allows light from 13.5 to 16.6 microns to pass through it. The red circles are the averages that make it easier to see the changes over time. It's pretty remarkable that we were able to even get these measurements, considering the change in brightness during the secondary eclipse was only 0.1%. But MIRI was sensitive enough to detect changes up to 0.027%. The temperature, it was about 450 degrees Fahrenheit. This suggests that the planet has no atmosphere and there's no mechanism to redistribute heat between the night and the day sides of the planet.